Hi everybody, this is the lecture 11, and in the previous lectures we derived new model for the sampling effect of current mode control, and we went through the technical details about the Ridley's model. We discussed all the steps of derivation, and we conclude that derivation is legitimate and may be accurate and very practical. And in this lecture, we will be talking about the design aspect of this converter using this new model. Okay, so we designed this buck converter and boost converter based on the classical technique. In classical method, we just ignored the sampling effect, and now the sampling effect is reflected here, smeared here as the form of double pole at the half-tone switching frequency in the control to output transfer function, right? So it will affect something, but this change is very minor. As I said, we are keeping the result of the classical analysis. We keep the main frame, and this sampling effect can be considered as the add-on to the existing model. That concept is new, okay? In the previous analysis, some textbook, they treat the new model is entirely new thing, okay? Proposing some new analysis technique. That is not true, okay? Classical model was different from what I presented here, and I modified the classical analysis into this form because, and the reason for that, the purpose of doing that is I want to have one frame which can adapt the classical method and new method altogether by simply adding small term. Okay, all right. So we'll review the design of buck converter and boost converter based on this new design approach, which include the sampling effect. And the examples you are using is the same as the previous one we used for the classical analysis and design. So you want to compare the performance of two design, classical design and the new design. It looks different, but there is a good reason for that. Okay, I'll address that during this lecture. Okay, so this is the circuit diagram of buck converter we used in the previous lectures for the classical design and the performance evaluation. So this remained the same, everything remained the same, and the difference is in current knob design. Okay, in the classical analysis, we used the omega ci is 0 dB crossover frequency of current loop was 0.1 from 0.1 to 0.3 times omega s. Okay, this is the approach we have taken in the classical design, right? But this one, in this new method, we are not using this, and we are just controlling this QP, right? QP determines the magnitude of peaking of the loop gain at the half-tone switching frequency. That peaking should be minimized or controlled. To have that, the QP of 1 is very good design. So we select QP as 1, and this is the expression of the QP. If you select the QP as a constant, then this SE is determined from this equation, right? Because all the parameters are known, this one is known, this one is known, okay? So you select QP as 1, okay? Then relationship between this new design and the classical design is shown here, okay? I'm showing the result, final result in advance, right? Then this is the same as selecting omega ci is 0.5 times omega s. If you follow this design with due procedure, okay, then you come up with some design, and you take this and come up, you follow this classical design, then design result of the current loop. They are exactly same, okay? So this is a very good relationship, right? And I'll address this again and again. So this is the introductory statement about this. We'll prove this, okay? Then if you select this, everything is automatic. Then this is selected and Ri is selected in the classical approach with this number. Then everything is selected, and then slope of compensation lamp is this one, and the slope of magnitude of the lamp is this one. Then MC is the parameter neatly defined, and 1 plus SC divided by SN. Okay, here this is relatively small, one tenth of this. Then this is very close to the unity, right? If this one is a unity, then SC is 0. That is the pure column mode control. Okay. If this number approach to 1, then this is the strong column mode control, means the nature of column mode control is very strong in this case. Right? I'm not talking about that is good approach. Right? Just this number very close to unity, then this is the strong characteristic of column mode control, and this number MC is larger than this number, maybe 1.5, then that is very similar to the voltage mode control, or the characteristic of column mode control becomes weaker. Okay, this is the classical design. We used classical design was something else, and at that time we select this. Okay, original guideline was omega Ci is some number between 0.1 and 0.3 times omega S. So we select this number, okay? Then we come up with this, okay? Then this one is much larger than this. This slope is about 10 times larger here. This one is 10 times larger than this, okay? That means it has some strong feature of voltage mode control, okay? And the column mode control feature becomes weaker, all right? So this is the weak column mode control with this number, with this large SE, it becomes similar to the voltage mode control, and the small SE, it has the strong nature of column mode control, okay? And according to this relationship, and there is a factor of the 2 difference, and this 0.2 times 2 is 0.4, and this design is same, exactly same. If you select this number in classical analysis, result is same as selecting QP 0.4 in the new design. Okay, you are using entirely different expressions, but somehow they are related with this by this relationship. Okay. We will prove this. It's not difficult to prove this. Okay. Then column loop is determined. Okay. And this is the previous one, classical design. And there are two different designs. One has a strong feature of column mode control, and the other one, original one, classical design, has weaker nature of column mode control. So it will be interesting to design performance of two converter later. Okay. Anyway, this is the buck converter loop shaping based on this new model. So we have this. Okay. Previously, we don't have this in classical analysis, and we have some additional pole. Okay. That pole is gone here, and this second order pole, double pole, is coming in, and this is the same structure for the voltage feedback compensation. And the thing is, voltage loop design, this guideline is exactly the same as previous case. Previous case in classical analysis, we select this. Why we select something different? There is no reason for doing that. This is the best design. Okay, so we select this. This is the good policy, and we select this, and then KV is termed like this. Expression is different. We have this KVCI, something like that, and omega CR. I think this was the same, all right? Then KVCI has this expression, okay? This is the KVCI of classical analysis we have some additional term as the fragment, as the debris. Okay, debris is fragment. Usually this fragment. Okay, because of the HES, there are some garbage is coming out. This can be considered garbage. Okay, and if you compare this is 1 and this number, I calculate this morning, then it is like this. I calculated this yesterday. So comparing this one is nothing. Okay, you ignore this, and omega PL. This is the expression of classical analysis. We have some additional debris, garbage here, and you have same thing. This C are the same, and we are comparing this unity, and we are comparing this. Okay, because this is common, this is common. Just compare this one, and this is this one. You can ignore this. Okay, you can keep this, but result will be the same. Okay, there is some round off error in here. Okay, so if you take the round off property, they become the same. Okay, so voltage loop design is exactly same as the classical design example. Okay, so only difference is slope of compensation length. So there is only one parameter we can play with. That is the slope of compensation length. Okay. So in new design, slope of compensation is reduced by 1/10. Okay. Somehow that is reflected in difference of loop gain and many other things. This is buck converter with new design. So we have this one. This is the result of the new design, and everything remains same. Everything remains same, and the classical design, it was this one. So this is the 10 times, about 10 times larger than this, or this is 10 times smaller than this. Okay, so it has strong nature of current mode control, and this is the weaker nature of the current mode control, or this one has a strong nature of voltage mode control, and this one has a weaker nature of voltage mode control. Okay, so it is reflected to the only this is the slope of compensation length, and this everything remains the same except that one. That is the point, and we are comparing this. We are using new model. Okay, new model contains This is the new design, and we are using new model and classical model. I'll explain details about this later. Okay, new model is taking care of sampling effect. It contains HES in the model inside, but classical model, it ignores HES, so there is a unity. Okay, there is no HES there, and the new model include feed-forward gains, and the classical model, they don't have feed-forward gain from the input voltage and out voltage. So it's two different models. But this one is prediction of the new model with this one, this blue curve, thick blue curve, and this thin black curve is prediction of classical model, and this thin black line is computational method. Okay, so only difference is coming up this point. But when you are evaluating the loop gain crossover frequency, which is 3 kHz, phase margin is 75 degrees, fairly large. Because this is buck converter, if you design boost converter, you cannot go this high. It is below 50 degrees, something like that. Okay, because of the RHP0 in boost and buck boost converter. Anyway, this crossover frequency is very high here. This is very high. Okay, and gain margin remain the same, and only difference is this one. Okay, there is some peaking here, some peaking, slight peaking. This can be considered as an exact one, maybe very similar to the experimental result, and this blue line is closer to this original one. So we have some improvement in the prediction of this high frequency characteristic of loop gain, magnitude, and phase. Okay, this is the prediction of the new model. This is the prediction of classical model. So there is a difference, but it really doesn't matter when you are considering this. Okay, it doesn't matter unless it goes up like this there's a big difference. One is stable, the other one is unstable. But other than that, this difference is not that meaningful. Okay? If you don't have new model, then you can do the computational method. And you see this. All right? Actually, the motivation of Ridley, probably he observed this peaking at the half switching frequency through the experiment, and he tried to fit his model to predict that at the peaking. On the peaking at the half switching frequency, intentionally, probably. I don't know. Okay? Okay. All right, so that's that. Okay. New design is evaluated using new model and classical model. So there is one design, and the new model and the classical model shows only difference at this high frequency, and this can be considered not significant, not important, or something like that for this case. Okay, and I compared the classical design and the new design using new model. Okay, forget about the classical model. All right. So I used the new model and I compared the classical design and the new design. There is a difference of the QP. Right. In new design, we are talking about QP, but the classical design can be converted in terms of the QP. Then this QP is 1.3 in new design. We select this number, and we select this in classical design, but it can be transformed to this 0.4. You just multiply this by 2, then becomes this equivalent. QP is 0.4. Okay, this is much larger than this, 2 times larger than this. Then this. Okay, so it shows peaking with this QP, and with this smaller QP, which is smaller than 0.5. That peaking double pole is not shown here. Maybe double pole is split into 2 real poles, and you are not seeing any peaking around that frequency. So it goes smoothly, but phase is affected. Okay, phase is affected, and the slope is changing, but peaking is not showing up here. All right. But if you take a look at this, with this new design with larger QP of 10. So this is the gain, phase margin is large, but because of the peaking, this gain margin is reduced. Okay, gain margin is, this is assumed this is a 180 degree, and the difference between 0 dB and the magnitude at that frequency is gain margin. So this design, gain margin is reduced compared to this, but phase margin is increased. Okay. So I write down here, this design has larger PM, yet it has a smaller GM. Okay, so it's not clear which one is better. Okay, so because there's a 2-fold difference between this. Okay, so that the advantage over this advantage of 2 different designs are not clear here. Okay, there are 2 different designs. Okay. We didn't select QP of 0.5. We select this, but it can be transformed to this. Okay? Then they are same thing. Because there is only difference in SE. If you select this one, then if you select omega CI equals 0.5 omega S, then you will get the SE of this new design. Okay? So they are same thing. Okay, they are same thing. There are no basic difference except this one. In the past, they all ignored this. They just looking at this. Okay? Then it really doesn't matter. This is the case of buck converter. Okay, and the closed performance I compared with new design and classical design, and I used the new model here. Okay, output impedance is almost the same. New design, classical design. Output impedance is almost the same. Okay, I used the new model to simulate this, but they are the same. Okay, so there is no impact in the output impedance. That should be true because at high frequency. This is just open loop power stage transfer function, and the loop gain magnitude becomes very small, then disappears. So this is the ESR is dominating here. They should be the same. Okay, this one is very interesting. Okay, audio susceptibility. This was classical design. This is the classical design with this large compensation slope. This is the new design with smaller compensation slope. Okay, the smaller compensation slope means this Ti current loop gain magnitude becomes large. Okay, so this is this input side or this input voltage side or front side of a converter, and you measure the current loop is here, and the disturbance is coming in the input side. So the current loop is working. So this Ti is here. This in new design, Ti is much larger than classical design. So we have more attenuation at low frequency only in the audio susceptibility case. So this is the benefit of strong current mode control with smaller SE. Okay. So most characteristics performance remain the same, but audio susceptibility becomes much smaller in new design that improve step input response. That is obvious. Okay, because the audio susceptibility is directly related to the step input response. So we are comparing this. This is the step load response of classical design, new design. They are same. Basically, they are same. Okay, we are comparing this step input response of classical design and new design. New design is much better. Okay, much better. Actually, this transient is within the ripple bound. This is a ripple, and this change is occurring inside the ripple. Okay, so this is the benefit of decreased SE or benefit of increased current loop. This is shown here. Okay, so audio susceptibility improved with the smaller SE, but this phenomena occurs only in the buck converter. Okay, boost and buck boost converter, everything remains the same. The reason for this is because of the structure of buck converter. Okay, buck converter has some unique structure. All right. I don't want to go through the details about this. It requires some time. Okay, so this kind of feature, this advantage won't occur in boost and buck boost converter. So there is no real advantage of increasing this Q in boost and buck boost converter. It only increases the risk of being unstable. Okay, so don't increase Q larger than 1 for any cases. Okay, and this is a boost converter example. Everything remains the same. It went through this. Okay, and again we select this. This is same as selecting this in the classical analysis, and you follow this in due approach, and you follow the classical approach. This steps are different, but result should be the same. Okay, and you come up with this result. And this is the classical design. In the classical design, we select this. That is the same as selecting this in new design. Okay, if you new design, you select this 0.5, then becomes QP is 1. But in the previous example, somehow I select this strange number. That is the same as selecting this. Okay, when you are comparing this and this has strong current mode control feature. This has the weaker current mode control feature. That will show up in their performance. And this voltage of design procedure, I repeat this. This is the case of classical design. This is the case of classical design. And you have unity, and this one is a 0.2. you can ignore this. And this is the case of classical design. And in due design, you have some garbage here, some debris, okay, which is very small. This is common, and I compared this number and this number. This number is 0.4. This is 0.2. Okay, 1/20, right? Ignored. Then everything remains same. Of course, this parameter should be the same. Okay, if you carry this term, it will be ignored here. You will have some 19.605, something like that. Then you ignore that, right? Comparison between classical model and new model. So this is the new design of QP equals 1, and I used the new model and the classical model. Okay, so up to this point, everything is the same. So this crossover frequency is 500 Hertz. Okay, much narrower than previous case. This is a boost converter. So boost converter is inferior to the buck converter in many cases because of presence of RHB0. Okay, so and phase margin is something like this. Okay, less than this 50 degree. I didn't watch carefully here, but this you can anticipate. Okay, this is what? This is 3. No. 30 plus 40 plus something. Okay, 50 is there is some bonus there. Okay, less than this one, and after this is a prediction of classical analysis. This peaking is not emerged here because it does not contain any term related with sampling effect, and this can be considered as the experimental result, and this new model is predicting this. So new model is showing this. Okay, that is the only difference in new model and the classical model. Right, and this is the result of output impedance prediction, new model and the classical model. Okay, so everything remains same, and there's a peaking. Of course, this is what 0 dB crossover frequency of the loop gain. That is the typical case. Okay, and this new model has something strange here. I cannot understand this. This is something is wrong with this the HES prediction. HES is good for many cases, but obviously this is not real run. Physically, it is not impossible here. This is not a switching frequency or anything. Maybe this have the switching frequency where this HES is playing the role. So, but this is way different from this measurement. So this new model has some problem. It is showing up here. Okay. Ridley, he does not want to see this. Okay, so his model has some flaw. Okay, and this is comparison of new design, classical design with new model. Okay, so the new design QP is 1, so it has some peaking. Okay, and in classical design QP was here, this one, so no peaking, and I overplot with the computational method or experimental result, so they match here, they match here, they match here, they match here, right? So new model is more accurate regardless of the value of the Q, small q, it provides the accurate result, large Q, smaller Q. Okay, so new model is accurate in this sense, right? But the design is very different because in new design I select this, and the old design I select the ratio between omega Ci and omega S, which is equivalent to this one. So the difference is showing up here. Okay, again phase margin will be, this one will be larger. The gain margin will be smaller, okay, because of this peaking. Okay, peaking hurt this gain margin. Okay, if the gain is increased by this much, this design becomes unstable. But with the same increment, this design remains stable because of the difference in this distance. Okay. All right. So, okay, this is the final conclusion. I told you this many times, right? So, we reviewed the design examples with this new model, including the sampling effect, and we went through all the design steps. Okay, so everything remains almost same except that compensation length slope. Right? This also highlight the importance of the SE, also highlight the limitation of this control method. There is one variable which we can play with in here. Right? Okay.